Welcome back to the GD&T Master Course, everyone. We're on Lesson 13 today, and we're diving into a concept that literally separates a perfectly functional assembly from, well, an expensive pile of scrap metal. We're talking about parallelism. Up to this point in the course, we've focused heavily on controlling the basic, standalone shape of individual features. But now it's time to figure out how to actually relate those features to one another using the ASME Y14.5 standard. Let's get right into it. Okay, picture this. You're manufacturing a linear guide rail. You measure it, check the specs, and hey, it's perfectly flat. It hits every single form tolerance on the money. But the second you try to slide its mating component onto it during final assembly, the whole mechanism binds up. It completely seizes. So why does that happen? Well, it's because while your rail might be perfectly flat, it is not parallel to its mounting surface. This brilliantly illustrates exactly why form controls alone just aren't enough. You can literally have a perfectly shaped part that still fails catastrophically just because its orientation is completely out of whack. Here's the quick roadmap for today's explainer. We'll start with an intro to orientation controls, define parallelism, and compare surface versus axis applications. After that, we'll break down the crucial difference between flatness and parallelism, look at real-world inspection methods, and wrap up with some common mistakes you absolutely need to avoid. Starting right off with Section 1, an introduction to orientation controls. So, what do we actually mean by orientation? Put simply, orientation controls define proper angles. They dictate exactly how a specific feature sits in relation to the rest of the part. And here's the kicker. Unlike form controls, which look at a feature totally isolated in space, orientation controls absolutely 100% always require a relationship to a datum. Think of your datum as your anchor to reality. It's a theoretical, perfectly exact reference point, axis, or plane that gives your part a functional coordinate system. Without it, you're just flying blind. Moving right along to Section 2, defining parallelism and its tolerance zones. Whenever you see those two parallel lines on a drawing, you're looking at a parallelism control. Essentially, this dictates that a surface, or a central axis, must remain straight at a distance. It's demanding that your feature perfectly mirrors the orientation of your foundational reference plane at a strict 0-degree angle. No tilting, no leaning, just a perfect 0-degree relationship. Let's break down how this actually looks on an engineering drawing. In a standard feature control frame, you've got your parallelism symbol, followed by a numerical tolerance, let's say 0.8 for this example, and then the letter A. That specific callout establishes a 0.8 wide tolerance zone. But here's the really important part. That zone isn't just floating randomly in space. It is strictly locked at a 0-degree angle to datum plane A. So your manufactured surface has to fall entirely within those two theoretical, perfectly parallel planes spaced exactly 0.8 units apart. Next up, Section 3, surface versus axis parallelism. You know, parallelism is incredibly versatile, but you have to remember that it behaves a bit differently depending on the geometry of the part you're dealing with. Surface parallelism is definitely the most common. It controls the orientation between two planar surfaces, which creates a tolerance zone made up of two parallel planes. Axis parallelism, on the other hand, controls how parallel a central axis is to another feature. We use this for features of size, think shafts or holes. Instead of flat planes, axis parallelism defines a cylindrical tolerance zone, and that entire central axis has to fit perfectly inside that imaginary cylinder. Now for Section 4, which covers a massive sticking point in the industry, parallelism versus flatness. Mixing up parallelism with flatness is arguably one of the most widespread and, honestly, most expensive misunderstandings in mechanical design. I can't stress this enough. These two controls serve completely different functional purposes. Flatness, that's a form control. It limits the deviation of a single, standalone surface, and it never, ever uses a datum. Parallelism, that is an orientation control. It fundamentally relies on a datum to function, creating those two parallel planes locked at exactly 0 degrees to your reference. When you compare their feature control frames side by side, the difference is crystal clear. A flatness callout stands entirely alone. It's just the symbol and the tolerance value. That's the whole shebang. But a parallelism callout, it always ends with a datum reference, like datum A. Let's say you apply a flatness tolerance when your design actually functionally demands that the surface be parallel to a mating part. Well, your parts might pass initial inspection, sure, but they are going to completely fail when they hit the assembly line. And if you think I'm exaggerating, the consequences of this specific mix-up are very real. There's this fascinating case study from a Cal State Sacramento thesis involving first-year engineering students. They were tasked with building a working steam engine. The whole project was practically ruined because the students manufactured mating components that were perfectly flat, but they weren't oriented parallel to their required datums. Because of that single orientation failure, the engines simply could not be put together. A tough but really valuable lesson.
All right, let's bring this into the real world with Section 5, Inspection and Real-World Applications.
So how does all this GD&T theory actually translate to the manufacturing floor? Well, you're going to see parallelism used constantly in aerospace, automotive, and heavy industrial machinery. We're talking about incredibly critical parts here: transmission shafts, bearing bores, and even things like SCORE International off-road racing roll cages. Think about a roll cage for a second. If you fail to correctly apply parallelism to those mounting joints, you get massive tolerance stack-up issues. A tiny, microscopic misalignment at one single joint multiplies as you move down the structure, resulting in a cage that simply will not fit the chassis. To actually verify these strict tolerances, quality engineers rely on a few specific tools. For simpler planar surfaces, the standard method is resting the part on its datum feature across a granite surface plate, and then sweeping a dial indicator across the controlled surface. It's super reliable. But for more complex 3D profiles, or when you're checking axis parallelism, inspectors have to step it up. They'll utilize highly accurate coordinate measuring machines, or CMMs, to digitally verify the exact geometry in three-dimensional space.
Finally, let's wrap up with Section 6, Common Mistakes and our Key Takeaways.
Let's look at some of the costliest pitfalls out there. There's a great quote from an experienced engineer that goes something like, "The problem with GD&T is that it isn't widespread enough. You can ask 5 different people and get 5 different answers." That is so incredibly true, and it perfectly captures why strict, standardized communication using the ASME Y14.5 standard is absolutely non-negotiable. Ambiguity in your drawings practically guarantees expensive miscommunication downstream.
Leading industry experts constantly point out that engineers love to shoot themselves in the foot by overcomplicating their designs. First rule, never pick imaginary points in space as your datums just because they look convenient on your CAD screen. Datums must be measurable, physical features. Furthermore, please do not over-tolerance non-crucial surfaces just to quote-unquote play it safe. If you slap a highly restrictive parallelism tolerance onto a surface that doesn't actually mate with anything, you're just going to cause perfectly functional parts to get thrown in the scrap bin. It drives up manufacturing costs for literally zero functional benefit.
So if you remember only one thing from today's explainer, make it your golden rule. Orientation matters just as much as form. You can manufacture a shape to total perfection, but if it's tilted the wrong way, your assembly will fail. Parallelism is your most essential tool for ensuring those parallel assemblies mate together smoothly because it locks a feature's orientation strictly to a functional datum at exactly 0 degrees. So, ask yourself, are the perfect parts sitting in your scrap bin right now failing simply because you relied on form controls instead of orientation controls? It's a $1 million question every mechanical designer and quality engineer needs to be asking. Next lesson, perpendicularity. Controlling 90-degree relationships.